In unit number 10, we're going to study 3D objects. So at the very beginning of the school year, we talked about one-dimensional objects. So lines, rays, those were all the one dimension. And then we talked about two-dimensional objects, circles and polygons and different things like that. And now we're going to move on to three-dimensional objects. And we get those three-dimensional objects by transforming two-dimensional objects. So when I say transformation, words that should come to mind are translation, rotation, dilation, and reflection. So we can do transformations to two-dimensional objects in order to get a three-dimensional object. So when we look at this first one, you have this picture here. What we did here was we took this triangle and we translated the triangle. So we took that triangle, and let's say we took that top one, translated down, and now we created this 3D object. Now you've studied these 3D objects before. This right here is called a prism. And the definition of a prism is a polyhedron with two congruent faces called bases that lie in parallel planes. Okay. So what I'm going to do right now is let's go ahead and I'll take my highlighter, box in this word bases. The base in this prism happens to be a triangle. So you see these triangles on top and bottom, they are parallel, or they lie in parallel planes. We'll draw little arrows here. So this is bases. We name prisms by their base. So because this base is a triangle, this is called a triangular prism. Moving forward, we're going to see prisms that are rectangular prisms, triangular prisms, so we can octagonal prisms, so we can talk about all different types of prisms, but we name that prism by its base. So if we look over here, I give you the transformation this time. I say we are going to dilate, specifically reduce, a square. So if we started with a square, here, I'm laying it flat, so it doesn't look quite like a square, but this is a square. So we'll take that. And we're going to dilate it to this point, meaning from here, we're going to make it smaller all the way till it gets to that point. Well, now you're looking at this, and we can see that this is a pyramid. Now, it doesn't look like pyramids that you are used to seeing, like the pyramids that we see in Egypt, for example, do not look like this. They're not slanted, but pyramids can look like this. So it's important that we recognize whether these pyramids are right pyramids or not. If they're right pyramids, they're going to be up, straight up and down. This one is not. It's slanted. We call this one a square pyramid because the base is a square. Oh, pyramid. There we go. So again, this is your base as well. Going to highlight that. And then this point right here is also an important point. That is called the vertex of the pyramid. The definition of a pyramid is a polyhedron in which the base is a polygon, so it could be any polygon, and the lateral faces are triangles with a common vertex. So in blue, this common vertex, that's this point right here. There you go. The base in this case is a triangle. And the lateral faces are these triangles that, sorry, the base is a square rather. The lateral faces are all triangles. Now when you're drawing three-dimensional objects, it can be pretty tricky to draw these, and a lot of people struggle with it, so I want to give you a couple pointers. When you look at this, realize that this back piece right here would actually kind of be behind. So it exists, this little edge exists, but if we say that it's behind it, we draw it as a dashed line, so we can say, oh, that's really behind it. And same thing with this one. This line would be behind, so we wouldn't really see it. So we can draw it as a dashed line. You'll see that we did that over here in the picture that was given. So just something to keep in mind. All right, moving down here. The next type of 3D solid that I want to talk about is a cylinder. I'll do all capital letters. Cylinder. The definition of a cylinder is a solid with congruent circular bases that lie in parallel planes. What I'd like you to do right now is think through what transformation could we do in order to get a cylinder. And there are multiple answers to this. Go ahead and pause the video and think through this on your own. Now that you've thought through it on your own, let's list some possibilities. You could take a circle and translate it. When you translate a circle, it's kind of like what we did for prisms, where you had the base was a polygon, but now we have the base is a circle, so we get a cylinder. Some people also would say that you could rotate a rectangle around one side, and you would get a cylinder as well. So in order to draw a cylinder, when we draw that, you draw it like this. I'm going to draw the sides here. And this again is where, because in the back you can't really see it yet, I'm going to draw that dashed line that shows that there is a side, an edge, but you can't see it, so it's in the back. The top, again, is called your base. The bottom is also called the base. But we could also have another type of cylinder. Imagine taking like a stack of pennies, and I don't have any with me right now, otherwise I would show them. But if you had a stack of pennies, and then they were straight up and down, and then you tilted it, that would still be a cylinder. So it would look something like this. So this is still called a cylinder. This is called an oblique cylinder, whereas this is a right cylinder. So I just want to make sure we discuss the difference between that. Moving on here, if I rotate a right triangle about one of its legs, well, let's picture what that looks like. If you have a right triangle, and I rotate about one of its legs, let's rotate about this leg right here. Picture what you would get. I have this here. It's like having that's a right triangle, and I rotate it about this leg. If I move that around or go like this, you can kind of see it. It's kind of tough to see, but you do end up getting a cone. So if I rotated that around this side, it would rotate all the way around, and this side would rotate, or you'd see the hypotenuse rotate too, and we would end up getting a cylinder. So if we rotated about that leg, you do get a cylinder. This right here is called a right cone, but just like with a cylinder, when you rotate, you get a right cone. I misspoke. But just like a cylinder, how you had a right cylinder, you could, and an oblique cylinder, you could have a right cone and an oblique cone. So with an oblique cone, you could get this by dilating a circle, just like we did with that pyramid, and you dilate a circle to a point, and now this is called an oblique cone. The definition of a cone is a solid that has one circular base and a vertex that is not in the same plane as the base. So notice, just like a lot of these things we talk about having a base, this guy right here is your base. And just like a pyramid, it will have a vertex. That's that point. It's important to specify that that point is not in the same plane as the base. And let's talk about why that is. So this right here is your vertex. Here and here. The vertex up and the top, we denote with blue, so I'll do the blue again. And the reason why that can't be in the base, or sorry, that vertex cannot be in the same plane as the base is because if it were, you would no longer have a three-dimensional object. It's now a two-dimensional object, which in this case, if it went straight down, that would just be a circle. So that's why we need to state that the vertex cannot be in the same plane as the base. And then finally, over in this last one, we have a sphere. And a sphere is very similar to a circle in two dimensions. If you think back to our definition of a circle, our definition of a circle is the set of all points in a plane equidistant from a given point. Well, the definition of a sphere is the set of all points, but not in a plane, this time in space. So that is a key difference between a sphere and a circle. In space, equidistant from a given point called the center of the sphere. So just like you had a center of a circle, you had a center of a sphere. So think through on your own right now, what transformation could you do in order to get a sphere? So what transformation to a two-dimensional object could you do to get a sphere? All right, now that you've thought on your own, let's talk through this. Well, if I want a sphere, it's going to be kind of related to a circle. What I'm going to do is I'm going to rotate a circle about its diameter. So if I take a circle, and I'm going to draw the circle kind of flat here, so I know it looks like an olive, what I'm saying is kind of tipped. I take the circle, I have the center, so this diameter is going through it, and I rotate about the diameter. That circle is going to spin up top and bottom. So this really right now should be a dashed line because once I spin it, you're not going to see it. This here is called the center, and I have a sphere. All right, so these are the five main 3D solids that we are going to be studying. There's a couple more vocab terms that I want to talk about. The first is a polyhedron. We use the term polyhedron in some of the definitions. It's important that we understand what a polyhedron is. A polyhedron is a solid that is bounded by polygons called faces that enclose a single region of space. So the faces are the polygons that make up kind of like the sides of these polyhedrons. So when you look up at these five examples, these two up here are polyhedrons. These are called polyhedral solids. But these three down here, the sides are not polyhedrons, or sorry, not polygons. They're kind of rounded, they're curved. So these are non-polyhedral solids. So let's clarify here. These are polyhedral solids, so making a polyhedron into an adjective. And these are non-polyhedral solids. All right, so a couple more vocab terms. An edge of a polyhedron is a line segment formed by the intersection of two faces. And a vertex of a polyhedron is a point where 3 or more edges meet. So I'm going to highlight these. What are colors I haven't used? I've got yellow and I got a green here. Okay, so vertex, I'll box it in green. Edge, I'll highlight in yellow. So when I go back to these polyhedrons, we only talk about edges and vertices of polyhedrons. So in this case, an edge, here's an edge, 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 another edge, and another edge. All those things that I highlighted in yellow are all edges. Same thing over here. This guy where those two faces meet, that's an edge. This is an edge, 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 edge. All of those are edges. Remember, vertices are where is a point where 3 or more edges meet. So here's a point where 3 or more edges meet. Here's a point where 3 or more edges meet. And now we see here are all of these 6 vertices. Over here we have 1, 2, 3, 4, 5 vertices. Those are all the vertices of those polyhedrons. Okay? Alright, so here's just a bunch of vocab for you. We talked about these 3 solids, and what you're going to do on your own now is flipping to the back. I give you 4 different solids. I want you to determine whether or not it's a polyhedron. I want you to name it if it is, based on how we talked about naming the polyhedrons on the front. And then, if it's a polyhedron, determine the number of faces, the number of vertices, and the number of edges that it has. So any of these that are not polyhedrons, you don't have to do anything to the right. So if you say no in this box, then you don't have to do anything to the right. Once you have answered those questions, I want you to write an equation to relate the number of faces, F, the vertices, V, and the edges, E. So in other words, this column is your F, here is your V, and here is your E. Look for a pattern and see if you can write an equation that relates the two. The next part, we need to talk about the definition of a cross-section so that you guys can do the last 3 examples. A cross-section is the intersection of a plane and a solid. So it is the intersection of a plane and a solid. So when you look here, for example, 2, it says describe the shape formed by the intersection of the plane and the solid. If you took that plane and you sliced that sphere, it's saying where will they intersect? What will that shape be, the intersection of the plane and the solid? So what I'd like you guys to do, again, do example 1, come up with your equation. To do example 2, 3, and 4, use this definition of a cross-section. And then go through and answer example 2, 3, and 4, and then we'll discuss this together as a class tomorrow. Good luck.